So hello everyone, welcome back to Hasvora Education. Today I am making this video because some of you were asking me to make a video on what is being expected in the tomorrow's paper of paper 34 practical. So I just recently went through the papers and I just compiled some of the questions that were not being tested in the recent years. So I expect them to come in the tomorrow's paper. They are from the oscillations from the question related to the water bottle, like measuring the rate of flow and about electricity. So now, without wasting any further time, let's begin. I solved some of the questions and I'll be explaining them and going through them because I want to save your time and I do not want this video to be much longer. So this question is the first one of and is being based on the oscillations. So just remember that it is a question one, like in this paper, like the paper from which I have uh, picked it up. It was a question one, but it can appear as a question two in your paper. So I'll also be going through the limitations as we discuss the paper. So now let's begin. The first question says, in this experiment you will investigate how the motion of a pendulum bob is affected by the height of the bob above the bench. Set up the apparatus as shown in figure 1.1. So now they have shown you the apparatus. It is a boss, a clamp, a thread and a bob. So you have to hold the thread between the clamp, and a bob will be connected to the thread. It is usually a bob made up of like a play-doh, and it is being you have to connect it. You have to just embed that thread in that dough and make a ball out of it. So that's actually a bob, and then you have to calculate the distance x from the bench and distance h is from the clamp to the bench. So now they are telling us that the distance h from the point of suspension to the bench should be as large as possible. The distance x between the center of the bob and the bench should be approximately 5 centimeter. Measure and record distance h. So throughout the experiment, do not change the distance h. So we have calculated as 95.0 centimeter. I I'll be using the assumption based values throughout this experiment because I have not conducted this experiment. I am just using some, you can say, um, you can say assumed values to carry out the working and show you how to perform these questions. So this is the h is 95.0 centimeter. As I told you, you have to calculate to the precision of the instrument, as the ruler gives you 2.1. So I have also taken the reading to 95.0 centimeter. Then they have told us to calculate the distance as approximately to 5 centimeter. So it can be 5.1, 5.2, 4.9. So it can be in the range, but it should be approximately 5 centimeter. Now, one limitation that I want to address here, that can actually come to us in if it comes as a question two, that can be that it is difficult to determine the center of bob. So now, what can be the improvement of this limitation? The improvement can be that we can measure the horizontal and the vertical diameter, and then we can take the point of intersection as the center of the bob. And you can also write that the bob is not a uniform sphere like that. And then you can also write that we can just make use a ready-made template, or you can say a ready-made sphere as a bob. And then we can calculate diameter both horizontally and vertically, and then divide it by 2 to calculate the center. So now let's move on. Now part B says, displace the bob small distance to the left, release the bob and watch the movement. The time the bob takes for each complete swing, first to the right and then back to the left as shown in figure 1.1 is t. So t is the time period for one oscillation of the bob. The limitation that here is the difficulty to know the start and the ending point of the oscillation. For example, if I release it from here, then I do not know that at which time does it comes to this point again. So this can be the limitation here. So what could be the improvement? We could use a position marker. Position marker is more of like, you can say, a wooden rod placed at a point that when it comes to this point, I'm going to stop. So this can be the limitation and improvement specific to this time period measuring. Then another improvement that can be is the small range of time for the time period. So what can be the improvement is that we could use light gates connected to the data logger to automatically stop and start the timer. So now they are telling us by timing several of these complete swings determine an accurate value of t. So by several of these complete swings mean that we have to take more than one swing and then calculate the time period for one swing. So what I did is that I took T1, T2. So T1 is the first 10 swings and T2 is the second 10 swings. So the first one comes out to be 14.37 seconds and it is for 10 swings. Okay, remember that. T2 is 14.33 seconds and it is for also for the 10 seconds. Then I took the average 14.35 seconds and then I divided by 10 to calculate the time period for one oscillation which they were requiring. So it comes out as 1.35 seconds. So as I told you earlier in the video of the practical tips that you have to take the video the the reading to the precision of the instrument. Like I have taken to 14.37 as the my stopwatch gave to two decimal places, but when you are calculating as I calculated the data time period, you are going to then maintain the significant figures, so it becomes 1.35 seconds. I hope it's clear. Now let's move on to part C. So part C says keeping h the constant, change x and repeat a part 3 and b. So what is a part 3 and b? A part 3 is the a part 3 is the distance x and b is the time period. Okay, so we have to repeat that and also include the values for t square in the table of results. So now what I did was I did not actually included the the value of 5 centimeter, but you have to because the examiner had clearly stated in the question that you have to begin from the 5 centimeter. But I just mistakenly forgot it to include it. So I kept a distance of 15 of a 10 centimeter in the value of x, like 15, 25, 35, 45, 55, 65. So whenever you are just keeping a difference, be very vigilant that it should be a constant difference. Like it should not be like 5, 10, 20, 50. Like it should not be a non-proportional difference. It, for example, if you are taking the 10 centimeter difference, then it should be 10 centimeter for all. And if you are taking 5 centimeter, then it should be 5 centimeter for all. Like for example, 5, 10, 15, 20, 25. And if in the case if you are taking 10 like I have, then it is going to be 5, 15, 25, 35, 45, 55, 65. But try to cover the range. Okay, so for each value of the for the x I have calculated the t1, the t2, and then I took out the value of the t average and then calculated the value of the time period. Likewise, as I mentioned, I kept the significant figures the same from for the calculated values like the t square, the t. So they are all in the four significant figures, while the individual readings are to two decimal places. So you also have to keep the values of the independent variable like the x which we are changing. You have to represent that in the ascending order. And ethically, you could also include the serial number like 1, 2, 3, 4, 5 just to keep an eye on the number of the readings. I have taken 7 readings, but the examiner requires you to keep 6 readings. I just took another extra reading for more just to keep my graph a little bit more accurate. Now, whenever you are plotting the graph, how are you going to find that how much should my one block represent? You are going to subtract the highest and the lowest value of on the of your x-axis. For example, my x centimeter, it is the highest value 75 and the lowest is 15. So I subtract it from each other, and then I check how many boxes have I been provided with in the x-axis. So here I have been provided with 8 boxes, and then I'm going to divide it by 8, so it comes out as 7.5. But 7.5 is will be much more of an awkward scale, and I will lose marks if I take one box as 7.5. Always take as 1, 2, 3, 4, 5, or 10. These are not awkward scales, and many of you will be thinking that the values are not actually in the range of 1, 2, 3, 4, 5, and 10 in most of the scenarios. In case if they are in decimals, then you are going to be maintaining 0.1, 0.2, 0.3, 0.5, and 1. And in case if they are in more decimal like 0.001, 0.002, 0.003, but you have to maintain like it is going to be 0.002, 0.001, 0.005, 0.01. You have to be in this range like 0.1, 0.2, and 5, and then 10. This is not an awkward scale. So that's why I've taken the 10 as my difference of each block on the x-axis. I also did the same for the y-axis. I just subtracted the value, the highest and the lowest values, and then divided by the number of the boxes, and then I plotted my graph here. Now, another thing when you are just plotting the graph of your best fit is that you have to keep the balance of the points. For example, you can see I have the 6 readings. I have balanced them on the line. 2 are on the left and 2 are on the right, and 2 are passing to the line. So I have keep the balance of the points. Now they are telling us to calculate the gradient and the y-intercept of this line of best fit. So for the gradient, what you are going to do is that you are going to make a large triangle. The triangle should be such that the hypotenuse of this triangle is going to be greater than the half of the length of the perpendicular line or the baseline. So make a large triangle, and then the point at which the triangle intersects the line, for example this point or the above point. So you have to check the reading at this point of the both the x and the y axis, and then you have to then you have to calculate the reading. So here I have calculated the gradient as y2 minus y1 divided by x2 minus x1. So my coordinates were 75 1.44 and 31 0.76. So the y coordinate is 1.44 minus 0.76, and then divided by the x2 minus x1, 75 minus 31, it comes out to be 0.1545. As the y-axis was t square, so its units were going to be second square, and the x-axis for the was centimeter, so it was going to be s square over centimeter. The units of the gradient were square over centimeter. So I recorded my gradient to 4 significant figures: 1.4545 into 10 power minus 2 s square over centimeter. Then they are telling us to calculate the line of the y-intercept. So as I used a false origin, then I could not extrapolate my line to calculate the y-intercept. So as I'm using the false origin, then what you have to do is that you are going to be applying the equation y is equals to mx plus c. So it is, then just plug in one of the coordinates, so it will give you the value of c. So the y-axis was a square, so I've just added 8 units as it was. Now the part E was about the quantities t and x are related by the equation t square is equals to a minus bx. So you know that y on y-axis we plotted the t square, so it was actually matching to the equation y is equals to mx plus c. But the gradient was b here, and a was equal to the y-intercept. So through this I actually found out what was b and what was a, and then I found out the ratio of a over b in the same way. So you could see that the s square were being cancelled, and a over b ratio was 18.21 centimeter. So this was the question of the oscillations that can be predicted. The second question is, in this experiment you will investigate the potential difference across a current carrying wire depends on its diameter. So as I told you that you can whenever you see 2 marks for one reading, the examiner is probably going to check for the average value. As the value of the wire or the diameter of the wire is very small, there is a large uncertainty, and he is gonna probably give you a micrometer for that. If he doesn't, that could be a possible limitation. Um, the one of the things that I actually missed was the two limitations for the previous one, was that oscillations do not follow one plane. It actually moves to the right and to the left. So what could be the improvement? We could use parallel guides to keep the keep the oscillation to one plane, and the other limitation was that could be applied to the question 2 is that two sets of reading are not enough, and the improvement could be take more readings of the dependent values to calculate the value of k and compare them. So now let's continue with this question. So what I did was I calculated the diameter. I took two values for the diameter. Diameter 1, which was d1, and its unit was millimeter. The d2 was also in millimeter, and then d average. So it came as 0.24 millimeter. So this was my millimeter reading for diameter. Then the part B said that connect the circuit shown in figure 2.1. The wire A should be connected into the circuit using the crocodile clips placed close to the ends of the wire. Then the part C said that measure and record the length L of the wire between the crocodile clips. So it was 45.0 centimeter as the assumed value. So one limitation that I noticed here, and obviously it is a question 2 here from the paper which I picked it up. So the limitation was that some of the wire length is being covered by the crocodile clip. So what can be the improvement? That you can just measure the length between the clips, and then you could um, add the length two times of the width that is being covered by the clip. Or you could also use narrower clips, or you could use a sliding jockey, or soldered wire. So there is no wire being covered by the clips. Another limitation that could be possible here is that there are kinks in the wire. There are kinks in the wire. So kinks means like the wire is folded in some of the places, which could add an additional length in the wire and also alter the resistance and the voltage that you are going to be obtaining from it. Now the part 2 says estimate the percentage uncertainty in your value of L. So percentage uncertainty in the value of L will be delta L over L into 100. So as I told you that the for each instrument the absolute uncertainty is going to be the least count divided by 2. So the least count to which the ruler gives you the value is 0.1, and it is divided by 2 to give 0.05. But as we take the measurement two times, like we one time we take a measurement at the zero scale, and then after which the value is obtained, for example 45.0 centimeter. So we multiply it by 2, so 0.1 it is obtained as an over as on as over absolute uncertainty. But we do not take this as our absolute uncertainty, because some of the errors also involved in it. we take the absolute uncertainty between the range of zero point 0.2 to zero point 0.5 centimeter. But I would just suggest that zero point 0.3 and zero point 0.4 are much safer values, so take them as your absolute uncertainty. So 0.5 divided by 45 into 10 into 100 is equals to 0.89% of the percentage uncertainty is there in the value of L. Moving on, part D says that close the switch, adjust a variable resistor until the current is close to 90 milliamps. Record the current I. So the current I was actually 90 into 10 power minus 3 amps, or you could also write 90 milliamps. Then we would record the voltmeter reading and then open the switch. The voltmeter reading was 1.50 volt. In the E part, they were telling us to measure and record the diameter D of the wire B. Also, I want to figure out one thing that in some of the voltmeters, the value is given to two decimal places, but in some there it is given to three decimal places. For example, the one I'm just assuming is it gives to two decimal places, but there are accurate voltmeters present that gives you three decimal places. Like it would give you a value like 1.607, but it could also be an error if the one with the two decimal places is given to you. So you could also write about that the voltmeter sensitivity is it is less sensitive, or you could say it gives value to 0.01, or in its improvement could be that you could use a digital electronic voltmeter, or the one which gives you value to 0.001. Then the part E says measure and record the diameter D of the wire B. So they have also provided us with another wire according to this experiment, which is going to be differing in the diameter, because they are going to be calculating the resistance and the things like that. So we just kept the diameter of the second wire a bit low. So it was D1 is 0.19 millimeter and D2 is 0.15. So the average was 0.17 millimeter. The F part said in this circuit replace the wire A with B, maintaining the same length. So the length was going to be the same, and between the crocodile clips in the C1, close the switch, adjust I to be the same value. So I was going to be kept 90 into 10 power minus 3 as they mentioned, and then we were going to be recording and then opening the switch. So as we decreased the diameter when we assumed it as a less diameter for the wire B. So you know that when the diameter decreases or the cross section area decreases, the resistance actually increases. So uh, there would be much potential difference or voltage change across it. So the voltage would be more. You do not have to think on this, because in the real experiment in the paper you will be provided with everything, and you are going to be just seeing the values as they are being displayed on the instruments. Now the part G says that it is suggested that the relationship between V, L and D is V is equals to K over D square, where K is a constant. Using your data, calculate two values of K. So as V is equals to K over D square, where K is the constant, so what could be the K? So we have to just multiply D square with the V and then divide it by L to obtain the K. So K will be equal to VD square divided by L. Then then measure the we will calculate the value of K for our first values of VD square VD and the L, and then K2. For the K2 we would use the other value, the 1.75, the 0.17, and the length was same for both. So we just plugged in our values and calculated is as three significant figures, because we also took the values of V, of D and L as three significant figures. So we are going to be maintaining the three significant figures unless and until there is a there is a problem of the preserving the difference between the values. For example, if the both values of the k are very similar to each other. So our k1 was being obtained as 192 to 10 power minus 9. Then I also calculated the units, as the V was in volt. So and the d square was actually in millimeter. That's why I have multiplied it with 10 power minus 3, and the 45 it was in centimeters, so I multiplied with minus 2. So it came as in meter. So the numerator was V into meter square and divided by the m of the meter. So it came as voltmeter. So it came as into volt into meter. The units were volt meter. So I just recorded the values 192 in 10 power minus 9 volt meter, and then uh, the the value of k for the yb was 112 into 10 power minus 9 volt into meter. Then they are asking to justify the number of significant figures that you have given for the value of k. I also told you how to write this answer in my video of the practical tips. So what I have wrote is that I have taken my value of k to three significant figures, as I have taken my value of v, l and d to three significant figures. Hence I also rounded off my value of k to the least number of significant figures that were being used, the three significant figures. So then they were asking us to explain whether the result supports the suggested relationship. So as this is a old question, so they have not provided us with the percentage uncertainty. And in the previous papers, we actually used to calculate the percentage uncertainty by ourselves. For example, if we were using the k was equal to vd square by L. So the percentage uncertainty in the value of k was actually equal to percentage uncertainty in the value of v plus 2 times the percentage uncertainty in the value of d, as it is being squared, and then plus the percentage uncertainty in the value of L. So this was how we would use to calculate it in the previous papers. But now they provide us with the estimated percentage uncertainty. So I had just assumed that the percentage uncertainty in this question was 15%. Then I calculated the percentage difference in the value of k, 198 10 power minus 9 minus 112 into 10 power minus 9, and then divided by the average of the two values, and then into the 100. So it came as 55.48 or 55.5% was my percentage difference. So what I wrote was, as my percentage difference in my value of k is 55.5%, which is greater than the estimated percentage uncertainty of 15%. Hence, my result do not support a relationship under the given experimental accuracy. So this is a proper structured answer to this question. Now let's come to the last part of this, which is about the limitations of this. So the first thing that we actually is that can be applicable to anything or any experiment is about the sets of the readings. So the two sets of reading are not enough to draw a valid conclusion. The other point that I also emphasized in the beginning was difficult to measure the length of the wire owing to the width of the clips covering the length of the wire. Third limitation could be voltmeter has a lower sensitivity, which adds uncertainty to the value of V. And the fourth one, the kinks in the wire introduces additional resistance in the value and provides inconsistent results. Now their improvements could be take more reading of value of VDL to calculate more value of K and then compare each. The second improvement for the length of the wire between the clips will be measure the length of the wire between the clips and add to the length of the width of the clips. So you can actually get the actual wire length. The third improvement could be use a voltmeter which gives value to 0.01 volt, or if e.g. I have provided the example of 1.607 volt. Then how could we could prevent the kinks? We could straighten the wire by hanging masses at the end of the wire. So this question is also finished. Let's move on to the next question. This is also from the electricity. So this question says, and it is also question number 1. So I have also already provided the limitations that could be actually that could be the possible limitations in the electricity question. Also there could be an additional one about the contacts that are made in the wire, that are about the contacts that are made in the wire. They could be dirty, like it has it its own resistance, which could give inaccurate results. So what could be the improvement of that? That you could use iron wool to improve its electrical conductivity. So now let's move on to this question. This question says that in this experiment you will investigate how the current in the circuit depends on the arrangement of the resistors within the circuit. You have been provided with a 447 ohm resistor with one unknown resistor. Connect the unknown resistor labeled X in series with 447 ohm resistor, an ammeter, a battery and a switch as shown in figure 1.1. So we have to make this setup and then close the switch and record the current I in the circuit immediately after taking the reading. Open the switch. So we just assume this value to be 0.56 amps, and then moving on, they told us that they are showing a number of possible combinations of the 47 ohm resistor together with the value of combined resistance. So they actually give us some choices that you have can what combination can you try for the resistances, and then you can measure the current. So the ones which are being embedded, or you can say encircled in the red box, these are the values that which I chose for the resistances, and then I represented them in an ascending order as it is the independent variable. So as I told you that I have measured these values to the precision of the instrument. The ammeter gave the value to 0.01, so I maintained the decimal places, and when I calculated the I over 1, as they told us to include in your table the value of R and I over 1. So as I calculate the I over 1, which units was going to be A minus 1, as A is being reciprocated. So as I calculated that, I maintained the number of significant figures, which was 3. So this was the table that was going to be made for the for this for this question. Now the part C told us to plot a graph of 1 over I, and its unit was going to be uh, amp minus 1 on the y-axis, and the r was going to be on the x-axis. In the same way as I did for the previous question, we are going to be finding out the range by subtracting the highest minus the lowest, and then dividing by the number of the boxes provided to calculate the number of the value of one box. So I will show you the graph I have plotted. This is the graph which I have plotted, and I have also highlighted the points so you can see it clearly that how I have balanced out my points, 3 on the left and 3 on the right. Then I for the gradient I just drew a triangle, large triangle, and then I took the points of intersection of the line and the triangle as my coordinates for the gradient. So then I calculated my gradient. My one coordinate was 20, comma 0.70, and the other one was 175, comma 1.50. As on the y-axis we had a minus 1, and on the x-axis we had ohms. So a minus 1 over ohm was over unit, over gradient came as 5.16 in 10 power minus 3, and we found out the y-intercept using the y is equals to mx plus c, as I used the false origin. So y-intercept was going to be 5.97 into 10 power minus 1, a minus 1, as it was the y-axis, and the gradient was 5.17 into 10 5.16 into 10 power minus 3, a minus 1 over ohm, or you could also write it as 1 over amp ohm. Moving on, it is suggested that the relationship between I and R is 1 over I is equals to R over P plus Q over P, where P and Q are constants. So use your answer to C2, determine the value for P and Q, give appropriate units. So as you could see that y was actually plotted on the the I over 1 over I was being plotted on the y-axis. So it is actually equal to the y, while the r was being plotted on the x-axis. So it means that 1 over p is going to be the gradient, while for the c is going to be equal to q over p. So what I did was 1 over I is equal to y, the gradient is equals to 1 over p, and x-axis is equals to the x value is equals to r. So through this, as we knew the gradient, found it out in the previous part. So it was 5.16 in 10 power minus 3 a minus 1 over ohm. So it is going to be just we are going to be swapping the places of p and the gradient. So p is going to be 1 over 5.16 10 power minus 3. So it comes out as 193.7, and the units as the a minus 1 is going to be in denominator, so you could just shift it to the numerator as it is a inverse, and ohm is already in numerator, so it becomes to three significant figure as 194, 194 ohms, amp ohms. And then we are going to be calculating the q. So the y-intercept is equal to q over p. We already know what is the p, and also the we also know the y-intercept. So 5.97 into 10 power minus 1 into 194 is equals to q. The units of the p was a minus 1 into not a minus 1, it was a into ohm, and the units of the gradient of not of the gradient of the y-intercept was a minus 1. So a minus 1 into a is equal, it just cancels out, leaving the ohm as the unit of the q. So q is equals to 115.8 or 116 as three significant figures. So this question is also done. Now let's move to the last predicted question, which is about a water bottle. So I'll be solving this question with you. So in this experiment, you will investigate the force exerted by the flow of water. You are provided with two plastic water bottles labeled A and B, with each with a hole in the base. So measure and record the distance h between the two lines marked on the bottle A as shown in figure 2.1. So we are going to be measuring the distance h between the two lines that they have already they are going to be already providing us with the two marks. So let's just assume it was 2.6 centimeter. Now in the second part, they are telling us to measure and record the diameter d of the bottle. So we are going to be just measuring the diameter by just the scale. This is going to be the diameter. Let's assume it is 6.7 centimeter. Now they are telling us to estimate the percentage uncertainty in the value of d. I was already told you that in the absolute uncertainty in the ruler is from 0.2 to 0.5, where 0.4 or 0.3 can be the safest values. So we are going to be taking 0.4 divided by 6.7 into 100. It comes out to be as 0.4 divided by 6.7 into 100. It comes out as 5.97%. So this is our percentage uncertainty. Now let's move on. Part C says that with the unused stand, clamp the bottle securely by its neck above the tray as shown in figure 2.2. The base of the bottle should be approximated 20 cm above the bench. So fill the bottle with the water. As the water flows through the hole into tray, measure and record a time t for the water level to fall from the upper line to the lower line. So this is going to be the upper line, and this is going to be the lower line, and we are going to be measuring the time when it just reaches the upper line until it reaches the lower line. So you have just seen that the examiner is also providing two marks here. So what does it mean that we are going to be drawing a table? Just let me draw a table. So we are going to be drawing a table, and we are going to be taking average. So this is going to be time 1 and time 2. So this is going to be one column, this is going to be the other column. So this is T1, this is T2, and this is T average. So this comes out to be 2.97, just assuming 2.97 seconds, and this is 2.92 seconds. So the, the average will be about 2.95 seconds. So this will be 2.5995 seconds. This is the time taken for it to fall. Now, what can be the limitations in this part? For example, when we were measuring the diameter, as it is made from plastic, the limitation one can be the bottle distorts or it squeezes. The bottle distorts. You could also add it squeezes when measuring diameter. The other limitation, which I believe could be a good one, can be that uh, it is to see difficult to see water level. For example, we it is as the water is transparent, so it will be difficult to see the water level due to reflection. So this could be the second limitation. Now we are going to be calculating the flow rate R of the water using the diameter and the T and the H. So R is going to be pi into D. The D was, I believe it was 6.7 into square into 2.6 and then divided by 4 into 2.95. So the units will be, this is centimeter, this is also centimeter, but it is going to be squared, so it will come out as 6 centimeter cube and then divided by the second. So let's calculate this. 6.7 square into 2.7 2.6 divided by 4 into 2.95. This comes out to be 6.7 into square into 2.6 into pi divided by 4 into 2.95. So this comes out to be 31.07. So I'm going to just round it off to 31 point or just 31, as I'm going to round it off to least number of significant figures that were being used in the H and in the D. So 31 centimeter cube per second. So 31 centimeter cube per second. This is going to be the unit. So when the water stops flowing, empty the water from the tray into one of the jugs provided. Then we are going to be refilling the bottle with the water and position the stand holding the water with the wooden strip so the stream of the water falls on the end of the strip as shown in figure 2.3. So we are going to be holding the water bottle from the place of its cap, and just like that it's the stream of the water touches the end of the wooden strip. Then when the water level is between the two lines on the bottle, so when it is the water level is between these two lines, for example these, when it is between these lines, we are going to be measuring and recording the height x above the tray of the mark on the wooden strip as shown in figure 2.3. So we are going to be measuring this. So let's assume this is 5.6 centimeter. Then they are telling us move the bottle so that the stream of the water is missing the wooden strip and measure record the height x2 above the tray of the mark on the wooden strip. So we have to move the bottle a bit, so that we have to move this point towards the left so that the stream actually misses this wooden strip and just passes vertically. So the height would be increased, so it would just assume it as 6.1 centimeter. So let's just assume it 6.1 centimeter. So in the fourth part they are saying that when the water stops flowing, empty the water from the tray into the jugs provided. Repeat A, C and D using the bottle B. So most probably they are going to be providing the water bottle B that is going to have the distance between the two lines that is going to be different from the first one, and it is also going to be having a different diameter. So let's just assume that in this water bottle has a shorter this has a shorter length distance between the two lines, so it is going to be 1.7, and the diameter is also small, so it would be about, just assume that it is 5.2, and the time would be, the diameter is small, so it would take less time. Okay, it would take less time, so it would be about 1.72 seconds. Also, we could also write about the time, as the time is has a smaller range, we could not actually accurately measure it. So what could be the improvement is that we could use a motion sensor, or you can say a light gate, or you could also say a video camera to record the 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 part when the water is moving through the bottle, and also with the timer in the view, so we could accurately measure when it comes to the upper line and to the lower line. Now let's calculate the r for this as well. So r was pi d square h over 40. So r is going to be pi into 5.2 square into 1.7, and then divided by 4 into 1.72. This is going to be pi into 5.2 square into 1.7, then divided by 4 into 1.72. This comes out to be about 20.98. So I would just take it as 21 cm cube over s. So one clue of what would be the unit of the flow rate is, flow rate is actually defined as the volume moving per second. So it is also cm cube over second. So the x1 will also just decrease. Let's just take the value a bit lower than the previous ones, as there will be less pressure. As there will be less pressure of the water on the wooden strip, so the x1 would be a bit higher, as it was 5.6. So let's take it as 5.8, and this the x2 will be 6.0, or let's just erase it. It could be 6.4. It could be 6.4 centimeter. Now in the F part they are telling us that the relationship between x1, x2 and r is x2 minus x1 is equals to kr. So k is going to be x2 minus x1 divided by the r. So as x1 and x2 are in centimeter while r is in centimeter cube per second, so what will be the resulting unit? It is going to be 1 over cm cube per second. So the per second will move to the numerator, and it will become second over cm cube. So let's calculate the k1. The first values were, the x2 was, just let's see what x2 was for the first one, 6.1, and the other one was 5.6. 6.1 minus 5.6 divided by the R. So what was the R? R was 31. So it was 31. While for the second one, it was 6.4 minus 5.8 and divided by 20. Now let's just calculate these values. So it is 6.1 minus 5.6 divided by 31. So it comes as 1.61 in 10 power minus 2, and this comes as 6.4 minus 5.8 divided by 20. This comes as 0. Just write it as 3.0 10 power minus 2. So the first value is 1.61 into 10 power minus 2 second over centimeter square, and the other one is 3.0 in 10 power minus 2. Do not write this one as we are going to maintain the significant figures to 2. So S over cm cube. Then explain whether your results support a suggested relationship. Just assume it is 15% here as well. We are going to be taking the percentage difference. So it is 1.61 in 10 power minus 2, and this is going to be subtracted from the other one. I just wrote it uh, in the first place, so I just added the minus sign to it. So 3.0 in 10 power minus 2, and then divided by the average of these. So 1.61 minus 1.61 into 10, it is going to be plus. So plus 3.02 in 10 power minus 2 divided by 2, and this is going to be multiplied by 100. So now let's calculate the percentage difference. 1.61 into 10 power minus 2 plus 3 into 10 power minus 2 divided by 2, and then 3 into 10 power minus 2 minus 1.61 in 10 power minus 1 power minus 2, and then divided by the average of these two values, and then into 100. So the answer comes out to be 60%. 60%. So I'm going to be writing that since the percentage difference in my value of k is 60%, which is greater than 15% for the estimated percentage uncertainty, thus my result do not support the suggested the or you can say the relationship under given experimental accuracy. So this was all for today. I have already told you the limitations. One other could be the two set of readings are not enough to draw a wide conclusion. Also, there could be that the bottle squeezes when you are measuring the diameter. The time period is very short. You could use a video camera with the timer in view to see when it reaches the upper and the lower line. The other could be that there is a difficulty in watching the water level when it comes to the upper or the lower line. So what you could do, you could use dyed or colored water, so that there you could easily keep an eye on the water level as it reaches the upper line. So this was all for today. I have made the video that people were asking for. like, share, and subscribe. Share it with anyone that you think it will help. I'll meet you in another video. Till then, goodbye.